of electricity, but it improves if ions get into it. Bath water, for instance, contains a number of ions derived from soap and from the salt in the body's perspiration. It is fairly good as a conductor. That is why it is dangerous to fiddle with electric equipment while in the bath. If there is a defect in the wiring, or if bare wires are exposed, electricity can be carried through the bath water to all parts of the body. Newspapers frequently tell of people who have been killed in this manner. Now that we have been introduced to the various elements, it is time to take a still closer look at them. In the next chapter we will see if the different atoms in an element are really all alike. Atomic twins. A close look at an element of the elements listed a few pages back. One of the most familiar is copper. All of us have seen that red-orange metal. Electric wires are usually made of copper. 1-cent pieces, or pennies, are 95% copper. Even 5-cent pieces, or nickels, which are silvery in appearance, are 75% copper. The other 25% is the element nickel, which gives the coin its color and its name. Now suppose we have a quantity of absolutely pure copper before us. By pure we mean that there is nothing in the copper except copper. No other metal, no other element at all, is present. What can we say about the atoms in that mass of copper? In the first place, all the atoms have the same atomic 53 number. The atomic number of copper is 29, and that means that every single neutral copper atom must have 29 electrons. If an atom has more or less than 29 electrons, it is not a copper atom. In addition, there must be 29 protons in the nucleus of each copper atom to balance the 29 electrons. Any atom that has more or less than 29 protons in the nucleus is not a copper atom. That takes care of protons and electrons, but there is a third kind of subatomic particle which we mustn't forget. How many neutrons are there in each copper atom? Here at last we find some variation. Some copper atoms contain 34 neutrons, and some contain 36 neutrons. To be exact, in any sample of copper that you can find, 69% of the atoms contain 34 neutrons, and 31% contain 36. The number of neutrons present in the copper atom makes no difference in the atomic number. That depends only on the number of protons in the nucleus. It doesn't make any difference in the chemical behavior of the copper atoms. That depends only on the number and arrangement of the planetary electrons. Does the number of neutrons make any difference at all, then? Well, the mass numbers of the two types of copper atoms are different. A 34-neutron copper atom has mass number 63, 29 protons plus 34 neutrons. A 36-neutron copper atom has mass number 65, 29 protons plus 36 neutrons. The two types of copper atoms are identified by these mass numbers. When a chemist speaks of copper 63, he means a copper atom containing 34 neutrons in its nucleus. When he speaks of copper 65, he means one containing 36 neutrons in its nucleus. Suppose you had a cubic inch of copper 63, containing 55 cents atomic twins, only atoms with 34 neutrons in their nuclei. How would it compare with a cubic inch of copper 65, containing only atoms with 36 neutrons in their nuclei? The two cubes would look the same. Both could be drawn into wires or pressed into pennies in the same way. The wires and pennies would behave exactly the same. If chemists treated them with acids or other chemicals, the two types of copper would act exactly alike. Copper 63 and copper 65 are atomic twins. But suppose you weighed the two. The cubic inch of copper 63 would have a mass of 5% ounces. The cubic inch of copper 65 would be more massive since each atom would contain 2 extra neutrons. All those additional neutrons would be enough to make the cubic inch of copper 65 have a mass of 5% ounces. There is only 1/8 of an ounce difference, but that is enough to show that atomic twins aren't completely alike. You'll find out, in future chapters, that there are other and more important differences between such atoms. Whenever two or more kinds of atoms differ from one another only in the number of neutrons in the nucleus, they are called isotopes. Copper-63 and copper-65 are copper isotopes. Isotopes many and isotopes few. You may ask why copper atoms have either 34 or 36 neutrons in the nucleus. Why not 35? Why not 37? Why not any number except 34 or 36? Well, let's see. You may remember that when we first talked about positive and negative electricity, we said that like charges repel one another. Protons all carry positive charges, so two protons ought to repel each other, and they do. Yet 29 protons can be squeezed together into the tiny nucleus of the copper atom and stay together. What keeps them from repelling one another and flying apart? Apparently part of the answer is the presence of neutrons. Whenever a nucleus contains more than one proton, it must also contain neutrons. What's more, every combination of protons requires at least a certain number of neutrons. In the case of the copper atom, 34 neutrons distributed among the 29 protons of the nucleus will keep that nucleus from flying apart. So will 36 neutrons. A copper atom containing either 34 or 36 neutrons in its nucleus stays put. It is stable. Any number of neutrons other than 34 or 36 fails to keep the protons together. If there were 35 neutrons, for instance, the nucleus would not stay put. A copper atom containing 35 neutrons, or any number other than 34 or 36, in its nucleus is unstable. Copper is therefore said to have two stable isotopes. Some elements can have more than two stable isotopes. The element iron is a good example. The atomic number of copyright iron is 26. All neutral iron atoms contain 26 electrons and 26 protons. Different iron atoms differ, however, in the number of neutrons they contain in their nuclei. Fully 92% of all iron atoms contain exactly 30 neutrons in their nuclei. These are atoms of iron 56. You can see that 26 protons and 30 neutrons come to mass number 56. The remaining 8%, however, include three different varieties of iron atoms. There is a kind with only 28 neutrons in its nuclei, iron 54. Another kind has 31 neutrons, iron 57, and still another kind has 32, iron 58. Each type of atom is stable. Iron, therefore, consists of 4 stable isotopes. In number of stable isotopes, the champion element is tin. It actually has 10 stable isotopes. Chemists can speak of tin 112, tin 114, tin 115, tin 116, tin 117, tin 118, tin 119, tin 120, tin 122, and tin 124. Any piece of tin you come across will contain a little of each isotope. If we look closely at the different elements and their isotopes, we may see an interesting point. Elements with an even atomic number, that is, with an even number of protons in the nucleus, have more isotopes than elements with an odd atomic number. Protons are easier to handle, apparently, if an even number of them occur in an atomic nucleus. They are paired off, and the nucleus then seems to be better balanced. At least, it is easier to stabilize such a nucleus by adding neutrons. The exact number doesn't seem to be very important. Most of the elements with even atomic numbers have 3 or more stable isotopes, which means that any of 3 or more different numbers of neutrons will do the trick. Iron, atomic number 26, has 4 isotopes, as we have said. So has chromium, atomic number 24. Nickel, atomic number 28, has 5, and tin, atomic number 50, has, as we just mentioned, 10. 50 protons in a nucleus can be stabilized by 62 neutrons, or 64, or 65, or 66, or 67, or 68, or 69, or 70, or 72, or 74. On the other hand, it is quite tricky to balance a nucleus containing an odd number of protons. After as many protons as possible have paired off, there is an odd proton left over. The odd proton makes the nucleus unbalanced or rickety. No element with an odd atomic number has more than 2 stable isotopes. In other words, for any such element there are, at the most, only 2 numbers of neutrons that will satisfy the protons and keep them from breaking up their association. Copper, atomic number 29, is one example, which we have already mentioned. Another is silver, atomic number 47. The 2 stable isotopes of silver are silver 107 and silver 109. Most of the elements with odd atomic numbers are even more particular than that. They have only 1 stable variety of atom apiece. An example is aluminum. Its atomic number is 13. The nucleus of its atom, to be stable, must contain 14 neutrons, no more and no less. No other number will do. The only stable atom variety of aluminum is therefore aluminum 27. Similarly, the only stable kind of arsenic, atomic number 33, is arsenic 75. The only stable kind of iodine, atomic number 53, is iodine 127. The only stable kind of gold, atomic number 79, is gold 197. And so it goes. Sometimes, an element with only 1 stable kind of atom is said to have only 1 isotope. Actually, though, the term isotope should only be used where an element has 2 or more varieties. Each single variety is called a nuclide, so you can say that aluminum, for instance, consists of a single nuclide. There are even some elements that have no stable atoms of any sort at all. Actually none. Not one. This may puzzle you and raise several questions in your mind, but be patient. We'll talk a good deal about this later on. Of the 103 known elements, 23 possess no stable isotopes, 20 possess 1 stable isotope, and 60 possess 2 or more stable isotopes. Altogether there are 266 different stable isotopes known. It is possible for 2 different elements to have isotopes of the same mass number. For instance, all calcium atoms have 20 protons in their nuclei and all argon atoms have 18 protons. But some calcium atoms contain 20 neutrons as well, while some argon atoms contain 22. The calcium atoms that contain 20 protons and 20 neutrons make up the isotope, calcium-40. The argon atoms with 18 protons and 22 neutrons are argon-40. 2 atoms which have the same mass number but different atomic numbers are called isobars. Calcium-40 and argon-40 are examples of isobars. Heavy hydrogen and heavy water. The simplest atom that can exist is that of hydrogen. Its atomic number is 1. It has only a single electron. Its nucleus contains a single proton and, in the commonest kind of hydrogen atom, nothing else, no neutrons at all. Such a hydrogen atom has mass number 1 and is therefore called hydrogen L. Does hydrogen possess any other isotopes? The answer is yes. An atomic nucleus containing 1 proton and 1 neutron is also stable. An atom possessing such a nucleus still has atomic number 1, since there is still only 1 proton in the nucleus, and still has only 1 electron. Such an atom is still hydrogen. Its mass number, however, is 2, 1 proton plus 1 neutron. It is therefore called hydrogen 2. Hydrogen 2 occurs in ordinary hydrogen gas in very small amounts. For every atom of hydrogen 2 in hydrogen, there are 5,000 atoms of hydrogen 1. The interesting thing about the hydrogen isotopes is that they are more different in mass than the isotopes of any other element. This may surprise you. You may say that the hydrogen isotopes differ in mass by only 1 unit. The 2 copper isotopes, copper 63 and copper 65, differ by 2 units. 2 of the tin isotopes, tin 112 and tin 124, differ by 12 units. Why are the hydrogen isotopes so special then? You see, a small difference among small numbers is much more important than that same difference, or even a slightly larger difference, among large numbers. Suppose that you showed a youngster 2 heaps of marbles, in one of which were 63 marbles and in the other 65. Without telling him how many marbles are in each heap, you ask him to tell you which heap is larger. The question would probably puzzle him. He would have to guess, or, if he were completely frank, he would say that they looked about the same to him. The situation would be the same if one heap contained 112 marbles and the other 124. That is the sort of situation we have with the copper and tin isotopes. Copper 63 or copper 65. Tin 112 or tin 124. The mass numbers are so large that a difference of 2, or copyright even 12, isn't much of a difference. Now suppose the same youngster is faced again with two heaps of marbles, one containing a single marble and one containing two marbles. Ask him again which heap contains more marbles. A glance is sufficient this time. The difference between 1 and 2 is much more obvious than the difference between 63 and 65 or between 112 and 124. In short, the difference between hydrogen 1 and hydrogen 2 is only a single unit, but the numbers are so small that that single unit is enough to make hydrogen 2 twice as massive as hydrogen L. Another way of looking at it is this. We've already said that a cubic inch of copper 63 has a mass of 5% ounces, while a cubic inch of copper 65 has a mass of 5% ounces. There is an eighth of an ounce difference. If, instead, we took 5% ounces of tin 112 and changed each atom to tin 124, the mass would become 545 ounces. There would then be about +3 of an ounce difference. But now suppose we take 5% ounces of hydrogen 1 and NOW19373_NOLOYD on Walnan at 2 if Chwain Diwali Yi 9 E1 Jawali E. Percentage UN SSYW pound at G1 SSYW 7 UN SSYW Yen WNIT 3H Centunit share ENJ Dauga SS3 DOLOS. I8 Wies AWOS Poet EESSE if A1 SSYW N 3J Doiga. Convert every atom to hydrogen 2. The mass becomes 104. It is exactly doubled. The difference in mass is not a fraction of an ounce, but a full 5% ounces. The greater mass of hydrogen 2 compared with that of hydrogen 1 is so noticeable that hydrogen 2 is commonly referred to as heavy hydrogen. The two hydrogens, in fact, are so different in mass that they have even been given separate names. Hydrogen 1 is sometimes called protium, from a Greek word meaning first, and hydrogen 2 is called deuterium, from a Greek word meaning second. The chemical behavior of the two hydrogen isotopes depends only on the number of their electrons. Since both possess only one electron, they behave very much alike. Despite their difference in mass, they are still atomic twins. Both, for instance, will combine with an oxygen atom to form a water molecule. The atoms in a molecule are sometimes alike, as in the hydrogen molecule or the oxygen molecule. Usually, though, a molecule contains atoms of different kinds. The water molecule, for example, contains 2 hydrogen atoms and 1 oxygen atom. The result is that there are water molecules containing 2 atoms of hydrogen L, a few which contain 1 atom of hydrogen 1 and 1 atom of hydrogen 2, and a very few which contain 2 atoms of hydrogen 2. The water molecules which contain hydrogen 2 are called heavy water because they are more massive than the ordinary variety. Heavy water is very rare. Only 1 molecule of water in 25 million contains 2 atoms of hydrogen 2. There is so much water on the Earth, however, that even this small fraction mounts up to a considerable total. How isotopes were discovered. We can talk freely about isotopes now, but it took people a long time to find out they exist. It is fairly easy to tell elements apart. Even in prehistoric days, people knew the difference between some of them. Primitive metal workers, for instance, weren't very likely to confuse copper and gold. If you had a sample of copper and one of gold before you wouldn't confuse them either. Copper is reddish, and gold is yellow. Gold is much more massive than copper. A cubic inch of copper weighs a little over 5 ounces, but a cubic inch of gold weighs about 11 ounces. If a chemical called nitric acid were placed on a sheet of copper, bubbles would form on that spot, and both copper and acid would turn green. If a drop of the same chemical were placed on a sheet of gold, nothing at all would happen. There are many other differences, too. All elements differ from one another in appearance and behavior. Usually the difference is even more noticeable than in the case of copper and gold. Chemists can take objects which contain a dozen or more different kinds of atoms and, by using various chemicals and instruments, can identify each element present and tell the quantity of each. This procedure is known as chemical analysis. The problem of isotopes is a much more difficult one. Different isotopes of the same element are so similar in appearance and behavior that the ordinary methods of chemical analysis can't tell them apart. Chemists first began to suspect that isotopes might exist in connection with the odd behavior of certain elements with particularly complicated atoms. I will begin discussing these elements in the next chapter. The final clincher, though, came in 1919, when two different isotopes of a single element were actually separated by J. Thomson, the English scientist who, 23 years earlier, had discovered the electron. He was working with the element neon, a rare, inert gas. Somewhat similar to helium. It occurs in small amounts in the air and is used in the neon lights with which we are all familiar. This is the way the isotopes of neon were discovered. An electric current was allowed to pass through a curved glass tube containing a small quantity of neon and nothing else. An electric current, as you know, is really just a moving stream of charged particles, usually electrons. The moving electrons often hit the neon atoms as they moved through the tube. Occasionally the electrons would strike an atom hard enough to knock an electron out of it. When that happened, the neon atom, minus one electron, became a positively charged ion. The neon ion, like any charged particle, moves under the influence of the electric current. Ordinarily it would move in a straight line. However, the glass tube is surrounded by a magnet which bends the path of the positive ions and makes them follow the curve of the tube. At the far end of the tube is a piece of photographic film, which the moving ions finally strike. When the film is developed, it shows a dark spot where the ions have struck. If all the neon ions were identical, they would all hit the same place on the film, and there would be only one spot on the developed negative. But the neon ions are not identical. Some of them are more massive than others. The more massive ions curve more slowly under the influence of the magnet. You remember the difference between kicking a moving billiard ball and kicking a moving cannonball, which we talked about in the first chapter. As a result, the more massive ions and the less massive ions hit the photographic film in two different places. There are two dark spots on the film after it is developed. Such an instrument, which separates ions of different mass and therefore reveals the presence of different isotopes, is called a mass spectrograph. Thomson's first instrument was quite crude. One of his assistants, however, the English chemist, Francis William Aston, improved it and made it capable of separating ions very finely and accurately. Aston received a Nobel Prize in 1922 for this. It is possible to calculate the mass of different ions from the exact positions of the dark spots on the negative. In that way it was found out that the neon isotopes are neon 20 and neon 22. Furthermore, the size of a particular dark spot depends on how many ions have struck. Scientists can therefore tell which isotope is present in greater quantity and by how much. The spot made by neon 22, for example, is much fainter than that made by neon 20. From this, it can be shown that 90.5% of neon atoms are neon 20 and that only 9.2% are neon 22. The remaining 0.3% are a third stable isotope, neon 21. All the other elements have been studied in this way or in similar ways since 1919, and their isotope composition has been determined. How isotopes are separated. A mass spectrograph separates isotopes into little heaps on the photographic film. The heaps are so small they are useless except to make marks on the film. Scientists who wished to study pure isotopes were eager to find a way of separating larger quantities. Fortunately, the differences in mass among the isotopes not only make the mass spectrograph possible, but also make large-scale separation possible. Different isotopes of the same element, as we have seen, behave the same way in a particular set of circumstances. The mass spectrograph direction of ion stream is bent by the presence of a magnet, lighter ions bending more sharply. Photographic plate lighter heavier airless tube isotope_isotope, neon 20, neon 22, strikes here neon ions are formed by an electron stream and travel as shown by dotted lines. But, and this is important, the more massive isotopes move a little more slowly than the lighter ones. The more massive isotopes go through the same motions as the lighter ones, but always lagging a little behind. You yourself would run more slowly if you were carrying a 10-pound weight on your shoulder than if you were not. It is the same with isotopes. An additional neutron or two slows them up. This difference between isotopes is useful to us in a number of ways. Let us consider water. The water molecule, we know, contains 2 hydrogen atoms and 1 oxygen atom. If an 67 atomic twins electric current is passed through water, the water molecules break up. Hydrogen and oxygen, which are gases, are liberated and bubble up through the water. But some of the water molecules contain hydrogen 1 and some contain hydrogen 2. Hydrogen 1, being lighter and more nimble than hydrogen 2, takes advantage of the electric current a little more quickly. The molecules containing hydrogen 2 lag behind and break up more slowly. Suppose, then, that a large quantity of water, hundreds of gallons, is subjected to an electric current until almost all of it has been broken up into hydrogen and oxygen. What would be left would be almost entirely water containing hydrogen 2, or heavy water, as it is called. You can see why this is so if you imagine a long race in which many contestants are entered. At the start, all the contestants, the faster ones and the slower ones, are jumbled together. By the time the end of the race approaches,